We're now going to take a second look at the chain rule and present a slightly different version of it that many would say is a more efficient way to utilize the chain rule. But in order to be more efficient, we have to use our powers of recognition even more. In other words, we have to look for the pattern that's required for using the chain rule and then apply it without a few intermediate steps. So to start, let's just remind ourselves of what the first version of the chain rule states. So it basically says if we have y that is a function of u and u that is a function of x, right? And again, why are we using different letters? Because they're more often than not different functions, right? And assuming differentiability, right, on some appropriate domain of both functions, the first version says that if I want to find the derivative of y with respect to x, then what I need to do is take the derivative of y with respect to u, so dy du, and multiply by the derivative of u with respect to x, so du dx, right? So again, not a very complicated rule, but the idea is recognizing when it needs to be used. Now, here the chain rule, this first version, it requires us to write the single function as two separate functions, right? But what if we decide to, cut out the middle variable, right? So what if we decide that we don't need the u, right? Well, let's see what that looks like, because we could take this expression, right, this function, and just replace it right there, right? In fact, it's that type of operation that leads us to choose this function u. So if we do that, then that leads to y equals f of g of x, right? That's the composite, right? So again, what we would like to be able to do is look at functions that are set up in this form, recognize this particular operation, and then be able to write down dy dx simply by looking at this and not having to use this kind of intermediate variable, this extra variable u, right? Well, let's take a closer look at this, right? And let's say if we were to write this using the prime notation. So instead of using the d's, let's take this side of it, right, this part, and try to express it using the prime notation for the derivative, right? So what does that mean? Well, if I switch this over to the prime notation, it would read y prime of u, right? Again, so it's like taking this equation and just writing y prime of u, and then would be the same thing right here. It would be u prime of x, right? And notice, so what I did there, I used the variables that are on the left side of each equation. So I'm expressing the derivative in terms of this. But equally, I can express it here. I could say f prime of u. So then this is f prime of u. And then similarly, differentiating u is the same as differentiating g. So I could replace the u prime with the g prime of x, right? Now, so if you notice what we're doing as we do this, right? And it looks like we're just playing around with variables, but what we're doing is we're slowly changing this form of the derivative into one that has now f and g. You notice we're close to that form, but then we can do one last thing. Since I plugged u equals g into this function to get this form, why not plug the same u equals g into that form, right? And then look at what we would get. It says it's like we would take the derivative of f and we would plug our g back in, so we would evaluate it at g of x, so that's another composite right there, and then we would multiply that result by the derivative of g of x, right? So this is actually the second form of the chain rule that doesn't require us to write down the letter u, right? And so let's actually just state that as a quick theorem and then spend the rest of the time doing some examples, right? So this is a theorem, and it's still our chain rule, just that now everything is in terms of x. There's no u anymore. So this is our chain rule version 2, right? And same kind of hypothesis. So we're going to say, so if f and g are differentiable both on some appropriate interval, right? So let's say on some interval, then y equals the composite of g of f and g, right, is also differentiable again on that appropriate interval, right? So when we compose two differentiable functions, we're going to get a third differentiable function. So then, now let's see what the second version says as far as writing down the derivative, right? So then this function is differentiable, and here is its derivative. dy dx is f prime, and basically I'm just going to rewrite this form. So f prime evaluated at g times g prime of x, right? So basically, let's see if we can say this one out in words, like we've done with the other rules for differentiation. So we have a composite, right? And again, I'll use a couple terms that aren't the best terms to describe this, but they work. So I'm going to refer to f as the outer function and g as the inner function because it's inside that additional pair of parentheses. So it's like you plugged g into f. So what the chain rule says is, let's say it out, it says you take the derivative of f, which is our outer function, and then evaluate it at the same inner function. So the inner function here stays the same, and then I then have to multiply that composite by the derivative of g, right? So I first take the derivative of the outer function, I do nothing with the inner function, and then I multiply that result by the derivative of the inner function, or g of x, right? So let's see if we can apply this rule with a few examples without having to label and identify u, right? Okay, so let's do some examples, right? And so yeah, let's start with something like, let's say 3x squared plus 9x minus 10 all to the, let's say, 10th power, right? And again, this is the type of problem where even though in theory we could write down 10 factors of this quadratic and just keep foiling and foiling and foiling until eventually we would end up with quite a few terms, right? Then we could do our term by term differentiation basically just using the power rule a ton of times. Well, again, that doesn't sound very efficient, and our goal is to make the process as efficient as possible, right? So let's see if we can write down what the derivative is, right? Now, as far as there are two functions here. The inner function, the function that's in the parentheses by itself is a quadratic, right? So that's like my g here, right? And then there's another function now that takes that whole quadratic and raises it to the 10th power. That's like my f. So my f is a power function, and my g is a polynomial, right? So let's see what it says. It says I should take the derivative of the outer function. Well, how do I differentiate a power? The way I differentiate a power is I bring that power down and then I subtract 1. So I'm basically going to do this, right? But I mean, doing that by itself is kind of crazy, right? Where are the x's? What do I do? Well, let's look at what this says. It says you keep g of x the same, so g of x doesn't change as far as what's inside the composite. So if I have 3x squared plus 9x minus 10 to the 10th power, then this first part of the chain rule says that now I'm going to have 10 times the same 3x squared plus 9x minus 10, but now that's going to be raised to the 9th power, right? So that's what this first part of the chain rule is telling us, is that we differentiate the outer function using whatever rule applies, in this case the power rule, bring down the 10, subtract 1 from the power, but you don't just do it with an x, you do it with the whole g of x still inside. So that's why we brought down the 3x squared plus 9x plus 10. But then there's more, because then it does say then take the derivative of the inner function and multiply what I have right there. So now I have to look at what's inside, and then I have to multiply by its derivative. So now I'm focusing on the 3x squared plus 9x minus 10. Its derivative is 6x plus 9, right? And then that completes the derivative of this composite, right? So if you look at it, you should see when you look at this part of it before we simplify, or even after we simplify, you should be able to see these two derivatives. You should be able to see the derivative of the outer function, which is the power function, and there is the power, right? Bring down the power, subtract 1. And then you should see another composite right here. This is not a product, but this is the derivative of the outer function evaluated at the inner function. So you plug your inner function back in, and then the other derivative that you should see is when you now multiply this factor by the derivative of what's inside the parentheses, right? So as far as simplifying, let's see what we can do. Not a whole lot, but there is one thing we can do, and we have to make sure we do it well. So first, let me actually write just the 9 for the exponent. So just doing the 10 minus 1. So we have to the 9th power, and then we have this quantity, right? Now what we have 3 quantities being multiplied. We have the constant 10, we have this quadratic to the 9th power, and then we have a linear function here. Well, I cannot distribute the 10 to this factor, because if you think about it, the order of operations says before I do any multiplication, I would have to evaluate any powers, any exponents, right? Well, the way I would evaluate this is by FOILing out the now 9 factors of 3x squared plus 9x minus 10. Well, again, that doesn't sound like much fun, but what I can do using the commutative property, I can switch these two factors around. So basically, if you have A times B times C, well, that's the same as A times C times B. So I'm going to switch places of the composite here and the linear function here. So then it looks like this. Now, this is not a necessary step, but I am justifying my next step in terms of what we can do to simplify, right? And again, we cannot distribute the 10 here because of this exponent that's not a 1, it's a 9. But now by doing that, I've kind of swapped places, but now I do have something that's raised to the first power, and now my distributive property does apply. So the way I can simplify this without going through the FOILing process is I can take the 10 and distribute it and get 60x plus 90 and then times the quantity 3x squared plus 9x minus 10 to the 9th power, right? And that's our derivative. And I consider this, this is a simplified form. Everything is nicely factored, and yeah, so that's our derivative, right? Let's try another one. Let's do something that involves a root. So let's say we have y that is the square root of e to the x minus 4x cubed, right? So let's say we have this function. Again, something that you might be tempted to do, but we can't do it because there's just no property, is that I can't take the square root of these terms separately, right? As a reminder, so here are here's something that you're not allowed to do. So if you have the square root of either a plus or a minus b, that is not equal to, in general, the square root of a plus or minus the square root of b. So in other words, you can't break the square root of a sum or difference into the sum or difference of different roots, right? So this doesn't work. The one that does work, maybe I'll put that in green to say this is good to go. What does work is if you have the square root of a product. That's equal to the square root of a times the square root of b. And that's also true if you have a quotient. If you have the square root of a over b, that's the square root of a over the square root of b, and there I'm assuming that b is not equal to 0, right? So as much as we would like to try to simplify this root, we can't, right? But what we can do is realize that the chain rule applies, because this is e to the x minus 4x cubed, and then it's all raised to the power 1/2, right? Now, having a fractional power like this, or if you had like a negative exponent, there would be no easy way to expand this, right? Now, there are some fancy techniques that would allow you to expand it, but you'd end up getting something that has infinitely many terms, right? In fact, that's a big part of what you'll study in the second semester of calculus, right? But for now, we just want to know how to find the derivative of this. So again, if I look at this, I see the composite. The inner function here, again, is everything that I have in parentheses. It's e to the x minus 4x cubed, all to the power 1/2. So now let's write down what the derivative is. So the chain rule says, again, start with your outer function, which is the 1/2 power. When I differentiate that, I'm going to end up with 1/2 coming down, and then when I subtract 1, I'll be left with an exponent of negative 1/2. And then the chain rule says, keep the inner function, so keep the e to the x minus 4x cubed, right? Right, so we have 1/2 times that quantity raised to the power negative 1/2. And then the second part now I have to multiply by another derivative. And that's the derivative of what's inside the parentheses, this inner function. So the derivative is e to the x minus 12x squared, right? And that is the derivative of our original function. Now, if we want to rewrite this so it has the first, positive exponents, and then eventually if we rewrite it as a square root, then it's going to look like this. I have that fraction as my coefficient, and then when I take the reciprocal, I'll have the e to the x minus 4x cubed And then that's all now to the positive 1/2. And then for the other factor that I have in the parentheses here, it's e to the x minus 12x squared, and I'll put that all over 1, right? Again, when you kind of put things either over 1 or under 1, then you get to see what are the numerators really. What am I actually multiplying? Well, in the numerator, it's 1 times the quantity e to the x minus 12x squared. In the denominator, it's 2 times this quantity times 1. So here is our answer as a single fraction, and I'll switch this denominator back to the square root notation. So it's e to the x minus 12x squared all over 2 times the square root of the quantity e to the x minus 4x cubed, right? So that's our derivative. All right, let's look at another example. And this one we're going to double up on the rules that we need. So take a look at this. Let's say I have 1 plus x over 1 minus 2x, but let's say that's all raised to the negative 4th power, right? So here's our function, and we can see that the inner function itself happens to be a quotient, right? And then the outer function again is a power. So let's see what it looks like when we differentiate this. Right? And this one will require 2 rules. To differentiate the composite, we'll start by using our chain rule. So take your outer function and find its derivative. Well, again, it's a power, so we're going to bring the power down, and then I have to keep the inner function as it is, and then subtract 1 from that exponent. And negative 4 minus 1 is negative 5. And then I have to multiply by the derivative of what's inside. But because what's inside is a quotient, I have to use my quotient rule, right? So now I have to switch gears and remember what the quotient rule says. Take the derivative of the numerator, which is 1, times the denominator, 1 minus 2x, minus the numerator, 1 plus x, times the derivative of the denominator, and that's just negative 2, and then this is all over the denominator squared, 1 minus 2x squared, right? And this is definitely not simplified, but again, just to remind you of certain things that you can do algebraically, let's see how much simpler we can make this. All right, so we got our negative 4 there. Now, even though the original function was given with a negative exponent, I'm going to show you how you can easily change that to a positive 5. Well, remember what a negative exponent implies, taking a reciprocal. So if I take the reciprocal of what I have in parentheses here, then I would have to change this negative sign to a positive sign. So I can do that. So then the 1 minus 2x now is in the numerator, and then the 1 plus x is in the denominator, but that negative 5 becomes a positive 5. All right? So you could say, well, that's our first step in simplifying. Now let's look at the numerator here, right? So as not to have to write too many extra things, let's look at just that. Well, if I distribute the 1, I'll have 1 minus 2x. Now I have a negative here, and then I'm also multiplying by a negative 2. So essentially, these two negatives will make everything here positive, right? So it's going to be a positive 2 and then plus 2x. All right? But at least that, so we see that this numerator simplifies a little bit because we have a negative 2x there and a plus 2x there. So the numerator, the thing I have boxed off in red, is just a 3. All right, so let's write that and say now I have 3 over the 1 minus 2x squared. Now that certainly looks a whole lot simpler, right? And now with the 3 there, that constant, and a negative 4 there, if I think of that over 1, I'll be able to multiply those two constants. I still can't distribute it into this fraction because of that exponent. And speaking of that exponent, there's something else we can do. All right, so let's see what progress we've made. So the negative 4 times the 3, that's negative 12. So I'll put a negative 12 out in front. Now, there's another property of exponents that says if you have a fraction, an entire fraction raised to a power, that's the same as taking the exponent raised to that power. I'm sorry, the numerator raised to that power and the denominator raised to that power. And I can do that with this. So this is the same as 1 minus 2x to the 5th power over 1 plus x to the 5th power. I already multiplied the negative 4 and the 3, so there's now just a 1 there. But then in the denominator, I still have 1 minus 2x to the 2nd power. But if you notice, in this numerator, I have the same 1 minus 2x. It's just raised to a different power. So what do we do with those powers? Again, properties of exponents. If I have a to the n over a to the m, then this is the same as a to the n minus m. So I essentially can subtract those powers and end up with 1 minus 2x to the 3rd power, which is going to be still in the numerator. So, I mean, we're making really good progress here, and this is probably as far as I will go. I'll say this is negative 12, and then I have the quantity 1 minus 2x raised to the 5 minus 2 power, so that's 3, and then this is all over 1 plus x to the 5th power, right? So just really an exercise in algebra, really, because I mean we got the derivative in one step, and granted, yes, we had to use two of our newer rules, that being the chain rule and also the quotient rule. Right? Okay, one more example, and this one is a lot simpler. Right? It's going to start out as a specific example, and then we're going to write down a very general result that's really helpful, something that you end up using a lot. So let's say you have something like e to the 5x, right? Much simpler function, but it is a composite, right? The inner function here is the 5x, right? And then the outer function will be the e. Right? So let's see what it looks like if we differentiate this. Well, again, recognizing that the inner function is the 5x, the outer function is the e, the chain rule says, first, take the derivative of the outer function. But we know differentiating the e keeps it doesn't change, right? And then the chain rule says, plug the inner function back in. So I'll have to have a 5x there, right? So that part is consistent with what we've done so far with our exponential function. But what's new now is that I don't just have an x in the numerator, or exponent, sorry. We have a 5x. So if I multiply by the derivative of 5x, that gives us 5, right? So the derivative of e to the 5x is 5e to the 5x. All I did there was just put the coefficient in front, again using the commutative property of multiplication. But what if we had to find the second derivative of this function, right? Let's differentiate it a second time. See what happens. Well, now we have an extra constant in front. So the constant multiple rule says that the 5 comes down, And then when I differentiate the e to the 5x, well, the same thing is going to happen. I'm going to get back e to the 5x, and then when I multiply by the derivative of the inner, again, I will multiply by 5. So now what I end up with is 25 e to the 5x, right? What does it look like if we did the third derivative? Well, our third derivative, it's going to be, right, so d3y dx cubed. So again, now the constant that's in front that comes down is the 25. Oh, 25. Let me write that more clearly. So we have our 25 there. When I differentiate the e to the 5x, I get back e to the 5x. And again, I have to multiply by the derivative of the inner function. You see, because the e to the 5x stays the same because of the exponential, the e to the x rule, that you'll always have an e to the 5x. And then you're always going to end up multiplying by 5 because of the chain rule. So we end up with 125 e to the 5x, right? And notice what you end up getting is, so for instance, this is a really nice pattern. Let me put a 5 there. You might say, well, how can you do that? Well, I can do that if I put an exponent of 0, because 5 to the 0 is 1. The reason why I'm doing that is because look at this, because this is then 5 to the first power, and then this is 5 to the second power, and then this is 5 to the third power. So every time, because you keep multiplying by a factor of 5 right here, you end up raising, essentially increasing the exponent of the 5. So if you were to differentiate a fourth time, you would end up getting 5 to the fourth power, which is 625 times e to the 5x, right? So the general case, which is very useful, it's something that you use a lot in many different types of problems. So like in general, we have a really useful result, and it basically says there's nothing special about the fact that it's a 5. If it was a 4, then we would do the same thing, but now we would have powers of 4. If there was a 1/2 there, it would be the same thing. It would be the same pattern, and you would have powers of 1/2. So if you have e to the kx, and let's just assume that k is a constant, so a real number, and just so that we don't get something trivial, let's assume that k is not equal to 0. So any other constant, and it even works if k is equal to 1. If k is equal to 1, then we're back to the very basic exponential rule that we established. But the key thing now is if I want to differentiate e to the kx, I will end up getting k e to the kx. Not only that, but we can actually write down a general rule for the nth derivative of this type of function. If we follow this pattern where the constant just keeps being raised to larger and larger integer powers, so the derivative there, the nth derivative of this function is going to be k to the nth power times e to the kx, right? So here is the first derivative, and it's such a nice pattern that we can actually write down a result for its nth derivative. And it's all because of the chain rule. And for the e, you have to pay special attention as far as recognizing when you have a composite and when you need to use the chain rule. All right? So definitely something to practice. So go practice, and then I'll see you in the next video.